We now consider the idealized for steady state process cycles shown in the picture provided here, in which state 1 is saturated liquid, and state 3 is either saturated vapor. Or superheated. This system is termed the Rankine cycle. And it is the model for the simple power plant. It is convenient to show the states and process on TS diagram as the picture provided here. TS diagram. The four processes are process 1 to point number 2, this point. Reversible adiabatic pumping process in the pump, and also here reversible adiabatic or isentropic pumping process in the pump. Constant pressure transfer, transfer of heat in the boiler, this process, constant pressure, and also in the diagram it is in this part. Process 3 to 4, reversible adiabatic expansion, in the turbine. Three to four. Isentropy is constant. And 4 to 1. Constant pressure, transfer of heat. In the condenser. As mentioned earlier, the Rankine cycle also includes the possibility of superheating the vapor as cycle. Let me provide the picture for the possibility of superheated. Possibility of superheated, we have the 1, 2, and 3 prime superheated position, and 4 prime and 1. One, two, if change of kinetic and potential are neglected, heat transfer and work may be represented by various area on TS diagram. If P potential energy approximately 0, we have work and heat on TS diagram. The heat transferred to the working fluid is represented by the area of the A the heat transfer to the cycle to the working fluid, the area of the upper line of our diagram for superheated position, for example, or for QE. A 2 prime 3 4 B, it is for saturated vapor condition, and the heat transfer from the working fluid is the lower area A 1 for Q out A 1 for B and A. This area. From the first law, we conclude that the area representing the work is the difference between these two areas. From first law, W is Q minus Q out, area of the shaded green and is 1 to 2 prime three, 4, 8, 1. As a result, the efficiency is from first law, the second bit QH. Area of 1, 2, 2 prime, 3, 4, 1, A1 for B, A. For analyzing the Rankine cycle, it is helpful to think of efficiency as depending on the average temperature at which is supplied and the average temperature at which heat is rejected. Rankine cycle efficiency depends on the average T average of Q in and T average of Q out. Any change that increases the average temperature at which is supplied or decreases the average temperature that is rejected will increase Rankine cycle efficiency. In analyzing the ideal cycle in this chapter, the change in kinetic and potential energies from one point in the cycle to another are neglected. In general, this is a reasonable assumption for actual success also. It is readily evident that Rankine cycle has lower efficiency than a Carnot cycle. The efficiency of Rankine smaller than the efficiency of Carnot. With the same maximum and minimum temperature as the Rankine cycle, because the average temperature between the point entering the cycle is different. We ask why choose the Rankine cycle as an ideal cycle, why not select the Carnot cycle. The main question is why a Rankine select that ideal and why Carnot not selected. because the temperature between 2 and 2 prime is less than the temperature during temperature evaporation. The first reason concerned with the pumping process state Y' is a mixture. The pumping process state 1' is a mixture of liquid and vapor. Great difficulties are encountered in building a pump that will handle the mixture of liquid and vapor at Y' and deliver saturated liquid at 2' here for a Carnot cycle. It is much easier to condense the vapor completely and handle only liquid in the pump. The Rankine cycle is based on this fact. The second reason concerns superheating the vapor. In the Rankine cycle, the vapor is superheated at constant pressure process 3 to 3'. In the Carnot cycle, all the heat transfer is constant temperature and therefore the vapor is superheated in process 3 to 3. Second, note however that during this process the pressure is dropping, which means that heat must be transferred to vapor as it undergoes an expansion process in which work is done. This heat transfer is also very difficult to achieve in practice. Thus, the Rankine cycle is the ideal cycle that can be approximated in the practice. In the following sections, we will consider some variation of Rankine cycle that enable it to approach more closely the efficiency of the Carnot cycle. Before we discuss the influence, we have some definition in the example. Some example and during this day's topic. Effect of pressure and temperature on Rankine cycle is the next section.